this set of notes, we're going to look at some different rules that make finding derivatives easier than applying the definition or using the geometric interpretation. All right, so the first rule we're going to look at is what is called the power rule. It's one of the most fundamental differentiation rules, and pretty much any time I'm taking a derivative, it's very likely I'm going to need this rule. And so the rule says if you're taking the derivative of a function that looks like x to the power of a, where a is a constant, then the derivative is going to be equal to a times x to the a minus 1 power. And your book provides a proof of the power rule, and so please read that proof on your own. So we're going to start out by finding the derivative of x to the fifth. So applying the power rule, if we want to find the derivative, what I'm going to do is notice in this case we have x to the fifth, so a is equal to 5. So using our rule, this is going to be equal to 5 times x to the 5 minus 1 power, which is equal to 5 times x to the fourth. All right, and now notice we could write this a variety of different ways using that notation from the last set of notes. And so, for example, if f of x is equal to x to the fifth, then we could also write the derivative as the following. And so here we're going to take the derivative of f of x with respect to x, and again this is still going to be equal to 5 times x to the fourth. If we were to write it as f of x is equal to x to the fifth, similarly we could write as follows. Now instead of writing f of x, I'm actually going to write what f of x is. And so again, this is going to be equal to 5 times x to the fourth. Now this particular notation, we're going to use this type of notation a lot in the examples that follow. Some other ways that we could write this is if we wrote the function as y equals x to the fifth, then we could write the derivative as y prime is equal to 5 times x to the fourth. Again, if we also wrote the function as y equals x to the fifth, we could also write the derivative as the derivative of y with respect to x is equal to 5 times x to the fourth. We don't always have to use the letters y and x. Maybe perhaps we could write t equals s to the fifth. So in this case, we would write the derivative of t with respect to s is equal to 5 times s to the fourth. And so just recognize there are just lots and lots of ways notationally to denote the derivative. All of these are commonly used. It really is just going to vary from source to source which notation is used, but they're all equally correct. And again, I don't really think one is more common than the other. I see all of these written in different places. All right. So our second rule that is very useful deals with taking the sums and multiplication. So the first rule says if you're going to take a derivative and you have a constant times a function, that's equal to the constant times the derivative of the function. And the second one says if you're taking the derivative of a function that is the sum of two functions, that is equal to the sum of the derivative of the two functions. And so we can use each of these rules and the power rule to help us take derivative. And so let's look at some examples here. So first of all, notice we have the function f of x is equal to 20 times x to the fifth plus 3x minus 4. And so by rule 2 that we have above, notice that if I want to take the derivative with respect to x of the function 20x to the fifth plus 3x minus 4, that is going to be equal to the sum of the derivatives. So I'm going to have the derivative with respect to x of 20 times x to the fifth plus the derivative with respect to x of 3x plus the derivative with respect to x of -4. Okay. Now next, by rule number 1, I can pull all of those constants out. So this is going to be equal to 20 times the derivative with respect to x of x to the 5th power plus 3 times the derivative with respect to x of x minus 4 times the derivative with respect to x of 1. Now, looking at this last term here, notice we're taking the derivative with respect to x of a constant, or just 1. In other words, there's no x involved. So this piece actually just becomes 0. Then, by the power rule, we can find the derivatives of the other pieces. So the first one is going to be 20 times 5x to the 4th plus 3. Now notice x is really x to the power of 1, so that's going to become 1 times x to the 0, which is just 1, so that becomes 3, minus 4 times 0. And so this becomes 100 x to the 4th plus 3. And we can do something very similar here. Now, one thing that becomes really important when we take derivatives is we always want to keep in mind which pieces are constant and which pieces we're taking the derivative with respect to. So here we're going to take the derivative with respect to x. So notice the cosine of pi over 6, that doesn't involve x. That's just a constant number. And then also the cosine of pi over 3 doesn't involve x, so that is also a constant. So again, we want to take the derivative with respect to x of 2x cubed times the cosine of pi over 3 plus the cosine of pi over 6. So first, we're going to apply rule number 2. And so this is going to become the derivative with respect to x of 2x cubed times the cosine of pi over 3 plus the derivative with respect to x of cosine of pi over 6. And then by rule number 1, this is equal to 2 times the cosine of pi over 3 times the derivative with respect to x of x cubed plus the cosine of pi over 6 times the derivative with respect to x of 1. And so just like before, we know that that second term is going to be equal to 0 because we don't have an x to take the derivative with respect to. And then we can apply the power rule. We get that this is equal to 2 times the cosine of pi over 3 times 3x squared plus 0. And so this becomes 6 times the cosine of pi over 3 times x. Looking at another example, and this example is going to help illustrate the importance of keeping in mind what is constant and what is not constant. So here we're going to differentiate the function with respect to x, assuming that a is constant. So since a is constant, it's going to act like any other constant number, 2 or 3 or a million. It's just a number that's constant, and we're taking the derivative with respect to x. So first, by rule number 2, we know that the derivative with respect to x of a squared x cubed minus 2a, that's going to be equal to the derivative with respect to x of a squared x3 plus the derivative with respect to x of minus 2a. And then by rule number 1, that is going to be equal to, now remember a is a constant, and so it's a constant, so a squared can come out of the derivative. Minus 2a times the derivative with respect to 1. And so again, our last term is going to go to 0 because there's no x to take the derivative with respect to. And then finally, by the power rule, we have that this is equal to a squared times 3x squared, which is equal to 3a squared x squared. In this next example, oops, zoom that back in. There we go. In this next example, we're going to find the tangent and the normal line, and I'll define what a normal line is here in just a second. Its standard form at the indicated point. So remember that in order to find a tangent line, or to find any line really, we need to know what the slope of that line is going to be. And we know that the derivative is the slope of the tangent line. So to start out here, the very first thing I'm going to do is take a derivative. So here I've got that y is equal to 3x squared minus 4x plus 7. And I'll let you check this on your own. This will be just like the examples that we just did. But the derivative is going to be equal to 6x minus 4. Now, this y prime, or this derivative, again, it's going to help me find the slope of the tangent line at a specified point. And so notice I'm interested at the point when x is equal to 2. So when x is equal to 2, I want to find both what y is equal and what y prime is equal to. Knowing what y is equal to will let me find a point that the tangent line goes through. And then evaluating the derivative at 2 is going to tell me the slope of the tangent line. And so those two pieces together are going to allow me to write the equation of the tangent line. So when x is equal to 2, if we substitute 2 into the function, notice we're going to have 3 times 2 squared, which is 12, minus 4 times 2, so minus 8 is going to be 4, plus 7 is 11. So when x is equal to 2, y is equal to 11. And again, evaluating the derivative at 2 is going to give us 6 times 2, which is 12, minus 4 is equal to 8. So y prime is equal to 8 when x is equal to 2. And so again, what this tells us is this is the slope of the tangent line when x is equal to 2. So using this information, we can then find the tangent line. So recall from the previous sets of notes, once we have the tangent line and we know the point that it goes through, we can write the tangent line by having y minus the function evaluated at the point, so in other words, the value of y, so y minus 11 is equal to the slope, which is 8, times x minus 2. And this is equal to y is equal to 8x minus 5. And then if we want to write this in standard form, we would have 8x minus y minus 5 is equal to 0. And notice to get that standard form, all I did was rearrange this piece right here. Right, so next, to find the normal line is just the line that goes through the point but is perpendicular to the tangent line. And so remember, a perpendicular line, to find its slope, we're going to take the negative reciprocal. And so to find the normal line, we actually do it the exact same way as the tangent line, except instead of the slope being 8, it's going to be negative 1 over 8. And so here, y is equal to minus 1 over 8x plus 10 and 3/4. And again, we could write that in standard form. And so in standard form, we would have negative 1 over 8x minus y plus 10 and 3/4 is equal to 0. And we get the standard form just by rearranging the form that is right above it. So now, just to kind of look at what that looks like on a plot, in green, we have the function. And you'll notice we're interested in when x is equal to 2. So when x is equal to 2, y is equal to 11. So you'll see that occurs at this point right here. The purple line is the tangent line. And then the black line is the normal line. Okay, so one last example for us to look at. So here we're going to find the tangent line with respect to x. But again, we're going to assume that a is constant. And one correction here that I need to make is this should also say at the point x is equal to a. All right, so again, if we're going to find the tangent line, the very first thing we have to do is take the derivative, because the derivative is going to tell us the slope of the tangent line at a particular point. So starting out, we're going to take the derivative with respect to x of x squared plus x over a plus 1. Now, keeping in mind that a is a constant by rule 1 from the previous page, we know that this is equal to 1 over a plus 1 times the derivative with respect to x of x squared plus x. And then by rule number 2, this is equal to 1 over a plus 1 times the derivative with respect to x of x squared plus the derivative with respect to x of x. And then by the power rule, this is equal to 1 over a plus 1 times, well, the derivative of x squared is going to be 2 times x plus, and then the derivative of x is just going to be 1. So this is equal to 2x plus 1 over a plus 1. So again, this is the derivative. It gives us the slope of the tangent line. And so when x is equal to a, because remember that's the point that we're interested in finding the tangent line at, and when we want to find this, we need to both find what y is equal to and what the derivative is equal to when x is equal to a. So notice that y, so in other words, I'm just evaluating our original function, is going to be equal to a times a plus 1 over a plus 1, which is equal to a. And evaluating y prime, or evaluating the derivative, is going to be equal to 2 times a plus 1 over a plus 1. So next we can write the equation of the tangent line just like we did before. So I'm going to have y minus a is equal to the slope, which is 2a plus 1 over a plus 1 times x minus a. And then from here, we could write that as, and I'm running out of space, so I'm just going to kind of write it over this blue line, y is equal to 2a plus 1, a plus 1 x minus a squared over a plus 1. So notice when we have this constant a, we're still doing the same things that we did before. It doesn't change how we take the derivative or how we go about changing the tangent line. or probably finding the equation of the tangent line, we just need to be careful and remember that we're taking the derivative with respect to x and that a is a constant.